Hey everyone, I welcome you all to the class of 5831 on the project presentation of in-vehicle canine safety systems involving real-time behavioral analysis of police canine units using Edge AI. I'm Siddharth and I'll be joined by my friend Raghu here, and we'll be walking you through our proposed solutions on reliable safety measures that overcomes the limitation of current industrial solutions for the safety of canine units. So these canines, they aren't just regular guard dogs. So they are highly trained and pose as a critical asset to the societal welfare. They do come with an initial high capital. Uh, Protecting them is not just a matter of life, but also operational readiness. But at times they do undergo certain situational distress, which eventually turns unnoticed. And we also do not have any sort of reliable solutions for monitoring their safety and maintenance. And vehicular heat stroke is one of the leading cause amongst that. And vehicular heat stroke is the second leading cause, in fact, for the non-hostile canine fatalities. This almost is responsible for like 20% of the deaths. And current solutions that are like the industry standards of it, they rely solely on the environmental check and sort of like the temperature sensors or just the visual behavioral analysis, but they don't do any sort of intelligence to understand how the canines are actually feeling or are they going through any distress. And they, in fact, you could say like they just monitor the vehicle and not the dog. And if a sensor fails or if a dog experiences a medical emergency, there is no alert triggered, or when the cabin pressure goes down, only then there is an alert trigger of some sort. So you would never know what happens to the dog. You would rather know if the conditions aren't met. So considering the semantic gap is the difference between measuring environmental data and assessing a biological reality. So the systems that are currently available, they just in turn ask if the car is hot rather than asking if the dog is safe. So they address the question of is the car is hot rather than the question of is the dog safe. So there isn't any intelligent awareness mechanism that has been posed so far, and we sort of have brought up a solution which could actually pivot in that direction. So to bridge this gap, we developed the K9 Guardian, the autonomous in-vehicle monitoring system. So it leverages a Jetson Orin Nano for Edge AI processing and uses YOLO 11 for object detection. A CSA camera captures the canine, and the YOLO model analyzes frames in real time. So the camera captures the unit and segments them into frames, and the YOLO model analyzes the frames in turn. So if the system detects sign of agitation or collapse, or let's say a fall of the canine unit, the a telegram message is sent immediately. So we've used Telegram as the message utility assistant, and it is directly paired with the officer's phone, and he gets an immediate alert if the dog is feeling any sort of distress or uncomfortable situation. So this ensures that the distress is detected regardless of the cabin pressure readings and provided actionable monitoring. So getting into the methodology, we have selected Ultralytics YOLO 11 Nano for the core model. This performs best in terms of edge computing, and also its lightweight architecture pairs great with Jetson Nano. So it also maintains a high mean average precision, which is sort of an addition to our solution. The model was trained on custom datasets of dogs in multiple locations of vehicle interiors. So it doesn't go around with a generic object recognition tech, but it also has a lot of data augmentations made, different set of dogs across like different vehicle interiors and stuff. So the data is very diversified so that it performs with like max accuracy. So coming now to the model training and transfer learning. So the training follows the split hardware workflow where we do the initial training of over multiple data sets across different conditions, across different augmentations, locally over a high performance GPU like RTX 3050. And then these model weights are being transferred to the Jetson where the real-time inferencing happens. So we also use transfer learning starting from the YOLO 11 in weights pre-trained on Coco, and that gets fine-tuned on our Kinect data set for like 100 epochs over 640 by 640 resolution across all images. So this sort of produces a model that is not only just accurate, but also it's efficient in terms of trying to emulate the real world patrol conditions. To help you more with the understanding of our model and the performance results, so I'll hand it off over to Raghu here. So he'll walk you through the further criticalities of how we designed the model and how the training and the architecture took place.
Thanks, Siddharth. My name is Raghu Nalapati. I'll be taking over the rest of the presentation from here. So before we go on to next slide, I would like to reiterate our slide number 6 again, which is the model training and transfer learnings. So we used a two-stage approach. So we performed the heavy training or heavy lifting on the desktop PC equipped with the NVIDIA RTX 3050. So we utilized transfer learning, taking a pre-trained model and fine-tuning it to our custom K9 dataset of 3,300 images tentatively and also 100 epochs. For 100 epochs, we also used mosaic argumentation to teach the model to ignore the metal bars of the cage, focus specifically on the dog animal if the animal is inside the cage, which is with the bars in the between. So the mosaic argumentation, let me go to next slide. Yeah, the mosaic argumentation. So as we can see from the screen that is projected, the box loss, the graph going down, the first one steadily decreased, the meaning the model learned to locate the dog accurately. And the classification loss also, we can see also the classification loss also covered, showing the model successfully learned to distinguish between our classes. So we also utilized mosaic argumentation to teach the model to ignore the metal bars of the police cage and focus only on to the dog behind them. Okay, let me go to next slide. Hardware optimization. Once we trained, we had to deploy to our edge side of the system. Initially, raw Python code was too slow, running at only 6 FPS. To fix this, we optimized the model using NVIDIA TensorRT, which is a light model, and also quantized it to a FP16 half precision. This gave us a massive 2.6 times speed up, jumping up to 80 FPS. So as you can see on the screen, especially the blue bar, the TensorRT implementation vastly outperforms the standard CPU GPU execution, ensuring we have a zero latency during an emergency situations like this, especially dog health failures. Okay, the next is results. Does it work? Here are our quantitative results. The model successfully draws bounding boxes around the dog, distinguished between states like sitting, standing, and also laying down. Especially the laying down, excessive laying down, we are implementing some logic in the Python to detect excessive laying down as a emergency situation for the dogs. So even with the complex lighting and occlusion from the cage bars, the detection remains stable and accurate. And quantitatively, our results are very strong. The most critical trick for us was a true positive rate for laying down class, which was achieved at 92%. Okay, this confusion matrix confirms the model rarely confuses sleeping with dead. So this high recall ensures that if dog actually collapses, the system will catch it. So if we can see the dark box, which is 58, is showing the high accuracy rate while we learn this neural network. Okay, let me go to next slide. Okay, coming to the officer alert or notification system. So finally, we integrated the IoT alert system. So we used Telegram bot API to send the alert. So this is actually once we have the dog posture is laying down for in reality it may be hours, but in current situations we have implemented a 30 seconds timer, so we can increment this timer in future as per our requirement and also the real-time conditions upon the dog behavior and health conditions, or we can tweak whatever we want in future. But currently we have a timer set for 30 seconds. Once the timer reaches to 30 seconds, it will automatically sends a notification within the Telegram application to the officer who is controlling the canine dog or canine car unit. So you can see, as you can see on the screen, the text message format that we formatted: canine alert, dog has laying down for 30 seconds. So like I mentioned, we can increment this 30 seconds timer to a couple of hours, so we can detect, the dog is laying down for a couple of hours, which is a bad sign. Then the officer have to attend the canine unit and take care of the dog. So in conclusion, okay, coming to the conclusion, we have built this privacy preserving and low cost safety layer that provides the redundancy to the mechanical systems. And for future work, so currently we are using RGB camera, which can only detect in ideal lighting conditions. But for future purpose, we would like to implement with the IR camera that can also detect some dark conditions, which is like nighttime, and also some dark situations like in cabin darkness. And also we would like to integrate all this data into the CAN bus system in vehicle, so that whenever this critical situation, all windows can be rolled down. So this is about our project. If there are any questions, we have included our email in GitHub and also the different parts of this project documentation. You can reach out to us. Thanks everyone.